If you're tuning in, you're looking for that shortcut to really getting a handle on complex ideas.
And today's idea is a big one.
Yeah, it really is. We're asking something fundamental. Is time actually real?
It sounds almost like, a philosophical riddle, maybe. But it's a serious question, really central to physics. For about a century now, many top scientists have kind of sided with Einstein.
Right, Einstein's famous line that the difference between past, present, and future is just a stubbornly persistent illusion.
Exactly, that illusion.
But we're not just going to accept that illusion today. Our mission here is to dive deep into Lee Smolin's work, specifically his book, Time Reborn.
Smolin makes a pretty radical argument. He says physics made a huge mistake when it decided time wasn't fundamental, a catastrophic one even.
So we're going to explore these two, well, clashing views. On one side, you have this static, timeless block universe idea that's dominated for decades.
And on the other, Smolin's picture. A dynamic, evolving universe where time isn't just real, it's the most fundamental thing there is, the engine driving change.
So for you listening, we're trying to get to the bottom of this paradox.
Huh.
Is the universe this fixed, four-dimensional block that just is?
Or is time actually flowing, carrying us along, constantly creating a new present moment?
Let's start at the beginning then. How did physics even end up ditching time? How did it write time out of the picture?
Well, it really kicked off with one of science's earliest, biggest wins, linking our messy, time-bound world to the perfect, timeless world of math.
Okay, like Galileo back in the 17th century, watching things fall.
Precisely. Falling objects, they seem chaotic, right?
Yeah.
Happening in time. But Galileo found they follow this perfect, unchanging mathematical curve, a parabola.
So the messy reality matched a timeless mathematical truth.
That was the moment, that cognitive leap. Describe something with math, and suddenly it moves from fleeting experience into this realm of eternal law.
So motion itself, which is all about time passing, gets kind of reduced to geometry, to algebra.
And Newton just cemented that view, didn't he? With his universal laws, gravity, calculus.
Right. If you know where everything is now, his laws supposedly let you predict the entire future. Perfectly. No room for change or chance.
Determinism, all built on this timeless mathematical foundation. But that whole approach needed a specific method, something Smolin really criticizes. He calls it doing physics in a box.
Okay, physics in a box.
Yeah.
Why the box, and what's the big issue with it?
Well, the box is necessary because, the universe is just too vast, too complex to study all at once. So physicists take a tiny piece, isolate, that's the box.
Like a lab experiment.
Exactly. You pretend it's totally sealed off from everything else, from the rest of the universe. That simplification lets you find these nice, clean, universal principles.
But Smolin says that's where the problem lies, that isolation.
It's a crucial flaw, yeah, because it forces you to make assumptions that aren't really true for the universe as a whole. You have to approximate.
And you need something outside the box, right? A clock.
Yes, that's critical.
Yeah.
You measure time inside the box using a clock that exists outside it. But if you think time should be a part of the universe itself, relational, internal, well, you see the contradiction. How can you apply that to the whole universe when there's nothing outside?
So the method itself imposes this external time. And then there's the final step, the sort of philosophical sleight of hand, where we take motion change happening over time and we freeze it. We put it on a graph, right? The line on the graph becomes the motion.
And the actual feeling, the experience of moments passing one after another, that just vanishes. It's removed for the sake of this abstract, predictable mathematical picture.
And that abstraction worked incredibly well for a long, long time.
For centuries, yeah. But Smolin argues when you try to scale that timeless view up to the whole cosmos, it starts to break down.
Badly.
And ironically, the biggest arguments for timelessness came later. From 20th century physics, Einstein's relativity. That's usually the trump card, isn't it? Time is just an illusion, like another dimension of space.
Absolutely. Relativity, both special and general, is seen as the strongest evidence against real time. It comes down to this concept, the relativity of simultaneity.
Explain that one. Why can't observers just agree on what's happening now?
Okay, imagine you're on Earth and I'm zooming past in a super fast spaceship. Because the speed of light is constant for everyone, no matter how they're moving, we will actually disagree on which distant events are happening at the exact same moment as our present.
So if a star explodes light years away, we might not agree on when it happened relative to us right now.
We literally wouldn't. My now slices through the universe differently than your now. There's no single universal present moment that everyone shares.
So time loses its absolute status. It gets tangled up with space.
It gets spatialized or geometricized. Yeah, it becomes just another dimension in a four-dimensional structure.
Which leads directly to this idea of the block universe.
Right, the block universe. It's a really profound, maybe even disturbing idea. It suggests the entire history of everything, Big Bang, dinosaurs, us talking now, the far future, it all exists together as one single, unchanging, four-dimensional block.
So the past isn't gone, and the future isn't yet to come. It's all just there.
Exactly. All moments exist simultaneously in a way. Our feeling of time flowing is just our consciousness moving along a predetermined path within this static block. Like reading a book, all the pages exist at once, but you experience them sequentially.
Wow. Okay, but the argument for timelessness gets even stronger, or maybe stranger, when you try to mix Einstein's gravity with quantum mechanics, quantum cosmology.
Oh, absolutely. That's where things get really weird. You end up with something called the Wheeler-DeWitt equation. It's an attempt to write down the quantum state of the entire universe.
What does it say about time?
Well, the problem is, when you follow the standard rules for combining gravity and quantum theory, the variable for time, it just vanishes from the equation.
It just drops out, disappears.
Poof, gone. Because in that framework, fundamentally, there's no external clock ticking away, and there's no fixed background stage for things to happen on. Space-time itself is part of the system.
So the equation describes a universe that doesn't change.
The quantum state of the universe, according to this equation, is static, frozen. It doesn't evolve or change, it simply is.
That feels so counter to everything we experience. And didn't Julian Barber take this even further, this idea of frozen moments?
He did. Barber's proposal is maybe the most radical. He says, forget flow, forget connections. All that truly exists is an infinite heap of these static moments, these snapshots of the universe, like individual frames of a movie piled up randomly.
So our sense of time passing, of cause and effect, that's just an illusion.
An illusion arising because some of these snapshots happen to have structures that look like memories or records of other snapshots. We piece together a story, but fundamentally, it's just a collection of static configurations.
It's philosophically elegant, maybe, but it feels like it completely ignores, well, us, our actual experience of now.
And that's the tension. Even Einstein felt it. He built the foundations for the block universe, but he admitted to Rudolf Carnap, the philosopher, that this experience of the now felt real, essential, fundamentally different from past and future.
And physics couldn't explain it.
No. And for Einstein, that was a huge clue. It meant science was missing something. It was incomplete.
And that very incompleteness, that dissatisfaction, is exactly where Lee Smolin steps in. He says this whole quest for a timeless universe started with a fundamental mistake.
He calls it the cosmological fallacy.
Okay, what's the fallacy?
It's basically the mistake of taking the laws and methods you developed for studying tiny, isolated parts of the universe, our physics in a box, and trying to apply them to the entire universe.
Wait, aren't laws supposed to be universal? Why can't we apply them everywhere?
Because the universe isn't just another box, it's unique. It is everything. There's no outside observer, no external clock, no surrounding environment to ignore. So when you take those timeless laws, which implicitly assume some kind of fixed background or external reference, and try to apply them to the universe itself, the whole system, Smolin says the theory hits a wall. It can't answer two absolutely basic questions.
Which are?
One, why these specific laws? Why this particular set of rules governing everything, fine-tuned as they seem to be?
And two.
Two, what set up the initial conditions? Why did the Big Bang start out the way it did? If the laws are truly timeless and eternal, they can't explain their own origin or the specific starting state of the universe.
Right. If they always existed, they can't explain why they exist in the form they do. That's a massive gap.
A huge explanatory gap. So Smolin says we need a completely different approach, a theory where there is no fixed background and where time is put back at the center, fundamentally real.
What does that kind of theory need? What are the requirements?
He lays out a few key principles. First, relationalism. Everything gets its properties only from its relationships with other things. No absolute space or time grid, just connections.
Okay, everything is relative to everything else. What's next?
Second, causal closure. Or you could call it No unreciprocated actions? Basically, all causes and effects have to happen within the universe. Nothing outside is allowed to influence it. Everything interacts dynamically with everything else.
So no pulling levers from outside the cosmos. It's a closed system in that sense.
Exactly. And the third principle is the real game changer. It breaks completely with how we've thought about physics for centuries.
Which is?
The laws of nature themselves must evolve over real time. They aren't fixed and eternal.
Whoa. Okay. The laws change.
Precisely. Smolin argues that's the only way we can ever hope to answer the question, why these laws?
Yeah.
They aren't just given. They are the result of some historical process of change, of evolution over cosmic time.
But hang on. If the laws of physics are changing, how can we even do science? Doesn't science depend on constants being, well, constant, gravity being the same yesterday as today?
That's the huge conceptual hurdle, absolutely. And Smolin knows it. His answer is subtle. Maybe the specific laws change, but the process by which they change might be governed by unchanging principles or a meta law.
Okay, so how does he propose? Yeah, this happens. How do laws evolve?
He proposes a mechanism called cosmological natural selection, or CNS. It's a fascinating, if speculative, idea.
Natural selection for universes. How does that work?
CNS suggests that universes can, in a sense, reproduce. Smolin theorizes this happens inside black holes. When a massive star collapses, maybe it doesn't just end there. Maybe it triggers the birth of a new baby universe somewhere else, perhaps with slightly different fundamental constants like the strength of gravity or particle masses.
The black holes are like cosmic wombs,
Yeah.
creating new universes.
That's the hypothesis, yeah. And just like in biology, the universes whose physical laws happen to be better at making black holes will reproduce more often.
Ah, so laws that lead to more stars, more collapses, more black holes get favored over time.
Exactly. So our universe, with its particular set of laws, might just be one that's highly optimized for making black holes, because those are the fittest universes in this cosmic evolutionary landscape.
Okay, that's a wild idea.
Yeah.
But what makes it better than, say, other speculative theories like eternal inflation, which also tries to explain our universe's properties?
The key difference, Molin argues, is testability. A lot of those timeless multiverse theories often rely on the anthropic principle, basically saying, the laws are like this because if they weren't, we wouldn't be here to ask the question. Which is hard, maybe impossible to actually test or falsify.
Right. It explains things by saying they have to be this way for us to exist.
But CNS, Smolin claims, makes concrete, falsifiable predictions. For example, it predicts specific limits on how massive neutron stars can get before collapsing into black holes. If astronomers find neutron stars heavier than that limit, then the CNS theory, as currently formulated, is wrong.
So it's vulnerable. It sticks its neck out with predictions we can actually check.
That's the goal. Vulnerable science, not philosophical speculation immune to evidence.
All right, let's assume Smolin is onto something. Let's explore the consequences. If time is real and fundamental, what does that universe look like? How does it feel different?
Well, first off, it brings back genuine novelty and maybe even freedom into physics. Smolin talks about the principle of precedence.
Precedence, meaning what came before matters.
Yes. The idea is that what happens next isn't just determined by timeless laws, but it's also influenced by what has actually happened before. The universe learns from its history, in a way.
So if you encounter a truly new situation, a quantum measurement unlike any performed before,
the outcome might not be predictable from existing laws alone. It could be genuinely new, genuinely undetermined until it happens. The future isn't just unfolding along a pre-written track, it's actually being created moment by moment.
That's a radical departure from the deterministic block universe.
Yeah.
And Smolin flips another concept on its head too, right? If time is real.
Then maybe space is the illusion, or at least secondary.
Wait, time is real, but space isn't. How does that work?
He suggests that time might be the truly fundamental layer of reality, and the space we experience, the 3 dimensions, the geometry that might emerge from a deeper level, maybe from this network of relationships and interactions happening over time.
So space isn't the stage. It's more like scenery that gets built by the actors.
Something like that. Theories of quantum gravity exploring geometrogenesis are looking into ideas like this, how space itself could arise from more fundamental, non-spatial building blocks interacting in time.
Okay, and finally, Smolin argues that we need real time to explain the universe we actually see around us, the complexity, the life.
Absolutely. Think about it. Our universe is incredibly structured and complex. Stars, galaxies, planets, life. It seems to be constantly building more intricate things. This matches what philosophers call the Leibnizian view: every moment is unique, rich, complex.
As opposed to,
As opposed to the Boltzmannian view, which comes from standard physics thinking about equilibrium. That view suggests the universe should be tending towards a state of maximum disorder, maximum simplicity, a kind of uniform heat death. Any complexity should be a rare, temporary accident.
but that's not what we see. We see stars forming, not just dissolving, life evolving.
Right. All that structure, all that self-organization requires constant energy flows, things being out of equilibrium. It proves the universe is fundamentally time asymmetric. The past is different from the future, and it's evolving away from simple equilibrium towards greater complexity, at least in pockets.
And that dynamic evolution, Smolin argues, absolutely requires time to be real and flowing. You can't get that kind of ongoing creation in a static block.
The existence of anything interesting basically depends on time being real.
So if we go down this path, if we accept evolving laws, we hit that really tough final question you mentioned earlier, the meta law problem.
Yeah, that's the big cliffhanger for 21st century physics, maybe. If the laws change, what rules govern how they change? Is there a deeper, unchanging meta law behind it all?
Because if there is, haven't we just pushed the problem up a level? We still have a timeless law, just a higher order one.
Exactly. We're back to asking where that law came from. It risks an infinite regress.
And if there isn't a meta law,
Then is the evolution of laws just random? Arbitrary? That feels unsatisfying, too. Finding a way through that dilemma, avoiding infinite regress without falling into pure randomness, that's the challenge, and maybe the biggest opportunity.
this has been quite a journey. We've really starkly contrasted these two realities, the elegant but maybe sterile block universe from classic physics.
Versus Smolin's vision, a dynamic, messy, evolving cosmos where time is the fundamental driver of everything new and complex.
And the takeaway seems to be that pushing physics forward means getting out of that metaphorical box. We need to grapple with the universe as a whole, with time at its heart.
And crucially, develop theories that are testable, that can be proven wrong by experiment. Not just elegant mathematics, but vulnerable science.
Which brings us, finally, back to ourselves, to our own minds. Smolin has this really thought-provoking closing idea about imagination.
He suggests our ability to imagine, to think about the future, isn't just some quirk of human consciousness. It's actually an adaptation to the reality of time.
Because if time is real, if the future is genuinely open and not predetermined,
Then being able to anticipate, to plan, to foresee consequences and act accordingly, that becomes incredibly valuable, essential even.
but think about huge challenges, like climate change. We can only even conceive of tackling it because we can imagine different futures based on our actions now. We operate within the flow of real time.
Our power to shape the future, however limited, hinges on that future being genuinely open, on time being real. It's not just an abstract physics debate, it connects to how we live and the choices we make.
Definitely something for you, the listener, to mull over. How does your own experience of this present moment, slipping into the next, fit into these grand cosmic pictures?